Electricity plays a major role in our lives, and as consumers we just expect it to work. The grid is made up of three parts: generating plants that traditionally produce electricity from combustible fuels such as coal, the transmission network that moves power long distances, often across state lines and sometimes international boundaries, until it reaches the wholesale customer, and then the distribution system that includes power lines, substations and transformers that move voltage up and down and vice versa until it's delivered to the end user. This powers our homes, our schools, our work and major industries. Well, oftentimes we don't pay attention to what makes all this electricity possible, but the US alone consumes over 3,000 terawatt hours of electricity annually. Just imagine, 26 billion light bulbs all ablaze for a year, and all of this energy is soaring above our heads and the scale is only increasing. What's even more amazing is that without a battery or storage system, a complex network is working that keeps inputs and outputs in balance. This miraculous network is our grid. Generation, that is the production of electricity, is also changing. In the past, generation was always on and predictable, but now the grid must handle population growth as well as the growth of new renewable forms of generation, like solar and wind. Well, these can go on and off as nature changes. As our cities grow, transmission and distribution lines are added at a high rate. Well, this creates a tangled mess. Instead of driving down a simple highway as we have before, we're now navigating a spaghetti junction for the first time ever. And it's only going to get worse with time. Keeping load flow balanced and distributed evenly across this increasingly complex grid is tricky. In fact, the balance of the grid has historically been maintained through the expenditure of excess transmission and distribution capacity and equipment, generally adding more lines. But even with all of these extra lines, if the grid becomes stressed or unbalanced, a disturbance or a blackout, as possible, can occur. We're constantly looking for ways to make our grid more efficient, more reliable, less expensive to maintain. We strive to obtain a smart grid. However, today the grid is anything but smart, and spending money on ever-increasing infrastructure in itself can't solve the problem of complexity. So we had to turn to computers and to math to help our hard-working grid managers. Grids are operated using a sequence of tasks that solve a problem in a finite time, and the current algorithms that operate the grid are based on what's called the Newton-Raphson method. Yes, as in Sir Isaac Newton. The Newton methods have been around well over 100 years. Why? They were a good tool, well understood, and in the absence of very stressed grids, they work fine. Why can't they work on stressed grids? Well, it turns out this Newton-based method relies on an iterative or an initial guess. And therefore, the data turns out sometimes to be correct and sometimes not. System developers have built many workarounds and improvements to help refine the results, but in the end, the fundamental problem remains. You can either completely trust the results or not. And especially during times of system stress, operators just cannot trust the results. Well, this causes a visibility issue. Just imagine driving on a 70-mile-an-hour interstate if the numbers on your speedometer began to get increasingly less clear above 50. If you drive over 70, you might get a speeding ticket. One would either have to sacrifice speed or safety. Well, this wouldn't have been a problem in the days when the system was easier and we didn't have even the capacity to reach such high speeds. Today, it's much more challenging. It turns out there is a better way. Gridquant is based on a set of new algorithms called the holomorphic embedded load flow method. Well, thankfully, we've made that shorter and called it HELM. HELM is based on patented and entirely new methods that arrive at a correct answer, or they tell you when one doesn't exist, regardless of your position along a voltage collapse curve, even in the most complex and stressed grids. That's right, 100% accurate. And since data is accurate, the models of our network can become much more accurate, and full visibility for our operators and regulators become possible. It's a giant leap forward to a smarter grid. And as if being right isn't enough, Gridquant has enabled disruptive capabilities for grid and grid operators that use HELM. It allows real-time visualization and GPS-like capabilities for decision support. And just like your trusty GPS, our system provides detailed instructions to solve limit violations and restoration problems, the most expensive and difficult to manage problems that our grid operators face. It even recalculates if a different path is chosen. Grid operators can now navigate the grid safely without relying only on investment in excess capacity or their long-term knowledge. Gridquant has effectively solved the visibility problem in managing today's complex grids while balancing the money and risk issue. Thanks to Gridquant, our operators as well as our planners and our taxpayers can drive and navigate through the grid network safely, efficiently and cost-effectively.